So in this video we're going to determine how you can calculate the total strain energy due to torsional loading in a solid circular bar. So if we are trying to find the total strain energy, we can evaluate the strain energy within a per unit volume times the differential volume, and we integrate that whole that product. So let's define our strain energy first. Our strain energy, we know for a torsional loading, is equal to the shear stress times the shear stress squared times 1 plus Poisson's ratio divided by E. And then we know that for our loading, the area is going to be constant if we find our differential volume along the length here. It might change as a function of x, but it's still going to be circular. So it might not be constant, but it should be circular across the section. And then our the differential element we're going to integrate over is going to be dx. Okay, so this torsional loading, if we look at it, is going to create a stress on our system, tau xy, here on the bar. Alright, so we know that for a torsional loading, the tau xy is going to be equal to the torque applied at both ends of the bar times the radius divided by the moment of inertia, the polar moment of inertia of the bar. So if we plug in everything into this equation here, so we plug in tau xy, the equation for tau xy, we end up getting that the torsional energy is going to be equal to this integral here. What we end up getting is we get we can break up this integral because we can break up this integral into two separate integrals. We can have one minor integral here, and then we can have another integral out here. So the blue integral I've highlighted in blue, this is only a function of dA, so only r squared is a function of dA. All these other terms are only a function of x. Okay? So we know that the definition of the polar moment of inertia is equal to this integral here. So because of that, we can substitute in j for that integral, and we can multiply it through. So we end up getting a nice simple integral that's only a function of x. So that's really nice. If the Poisson's ratio, the elastic modulus, and the shear and the polar moment of inertia are not a function of x, meaning it's a constant area along the length, our total strain energy is just equal to this algebraic equation here. Okay, so to sum up, what we did is using our original loading condition, we determined our shear stress, and we defined our volumetric element to then calculate the strain energy per unit volume and the volume and dV. We plugged it into this integral, and we plugged in the definition of shear stress due to torsion, and we were able to calculate the total strain energy by making a couple substitutions using the moment of the polar moment of inertia, and that's it.